friends, now we will continue with our topic divisibility. Okay. Before going to divisibility test, we will repeat one basic thing, that is representation of number. Okay. We know, suppose consider the number 789. If you want to represent this number in decimal system, we know we can write this 789 is equal to 7 into 10 to the power 2. So 100 into 7 is 700 plus 5 multiply 7 by 10 to the power 2, because 7 is at 9 is at unit place, 8 is at 10 place, and 7 is at 100 place. So 7 into 100. Okay. Then 8 is at 10's place, so 8 into 10 to the power 1 plus 9 is at unit place, so 9 as it is, or we can add 9 into 10 to the power 0, because 10 to the power 0 means 1. Okay. This is the decimal representation of the any integer or any natural number. So in general, any natural number m can be represented as ak 10 to the power k plus ak minus 1 10 to the power k minus 1 up to a1 into 10 to the power 1 plus a naught. Okay, where a naught is the unit place in the number, like this. 9 is the unit place, a1 is the 10th place, up to so on. Okay, so this is the general representation of any number. Okay. For example, 789, you can write 7 into 10 to the power 2 plus 8 into 10 to the power 1 plus 9 into 10 to the power 0. So any number m can be represented like this. Okay. So now we will go to divisibility test. Divisibility test. Now we have in general learned this test before our graduation also, but now we will repeat some test. Okay. The first test is divisibility by 2. Okay. Divisibility by 2. Divisibility by 2. We know an integer or a number is divisible by 2 if only its unit digit is divisible by 2. Okay, that is 2 divides n if and only unit digit is divisible by 2. That is 2 divides a naught. Okay, this is the divisibility by 2. Okay, we will prove this now. Okay, so now to the proof, very simple. We will write down the proof. We know any natural number or any number can be written like this. Okay, we have any natural number n can be written as, or any integer can be written as ak 10 to the power k plus ak minus 1 10 to the power k minus 1 up to a1 10 plus a0. Now see, each element a1 to 10, 10 is divisible by 2, then 10 square 100 is also divisible by 2, 10 to the power 3, 10 to the power 4, each number is divisible by 2. Okay, we know the rule. We have 2 always divides 10 to the power k for k greater equal to 1. But only problem is that in the last term a naught into 10 to the power 0 means 1. If there is no power of 10 for 10 to the power k for k greater equal to 1. So each term, this term is ak 10 to the power k, but there is 10 to the power k. So 2 divides 10 to the power k. So 2 divides ak 10 to the power k. Similarly, 2 divides this term also, because there is 10 to the power k minus 1. Similarly, up to so on, 2 divides 10 times a1, because 2 divides 10, so 2 divides a1. But only here there is just a naught. So 2 divides whole this number. If I leave 2 divides a naught. Okay. So this implies 2 divides each term in this summation except last term. 2 divides each term will give equation 1. Each term in 1 except last term a naught. This implies 2 divides n. If I leave 2 divides last term. If I leave 2 divides. So if I leave 2 divides last term. Okay. This is the very easy way. This is the divisibility by 2. Now we will say divisibility by 3. Okay. So next is divisibility by 3 or test of divisibility for number 3. Okay. Now the test is 3 divides an number or integer if only 3 divides sum of digits in that number. That is 3 divides sum ak plus ak minus 1 up to a1 plus h. Okay. This is the test of divisibility. That 3 divides a number if 3 divides the sum of digits in that number. Okay. So we will see proof now. Okay. So proof. So let 3 divides this sum ak plus ak minus 1 up to a1 plus a0. Okay. Now since 3 divides this sum, we know this number or this sum is multiple of 3 by the definition of divisibility. This implies ak plus ak minus 1 up to a1 plus a0 are equal to multiples of 3 or 3 times m. Okay. Or we can write this implies a0 is equal to, or we can write a0 is equal to, transfer the remaining part to the right side. A0 is equal to 3 times m minus ak minus 1 up to minus of a1. Okay. We have maintained a0 to the left side and transfer this other terms to the right side. So this 3m as it is minus ak minus 1 up to so on and minus a1. Okay. Now put this term, the value of a0 in the general representation of n. What is the general representation of n? You know we have n is equal to ak 10 raised to power k, okay, plus ak minus 1 10 raised to power k minus 1 up to a1 10 raised to power 1 plus a0. Now put this value of a0 to this equation here. Put the value of a0 is in this equation, that is here. This implies, so putting value of a0 we get n is equal to, now ak 10 raised to power k as it is, up to all the terms up to this are same as it is. So ak minus 1 10 raised to power k minus 1, okay, up to a1 into 10. Now put the value of a0 here. So a0 is 3 times m minus ak minus 1 up to minus of a1. Okay. Now see, here ak 10 raised to power k, here minus ak. So ak is common. Here ak minus 1, here ak minus 1 10 raised to power k minus 1, here minus ak minus 1 up to so on. So the terms, but taking common terms outside, we get, now here ak and ak are common. So here ak, here 10 raised to power k is multiple and here minus 1 is multiple. Okay. Similarly, plus A k minus 1 is also common. Here multiple is 10 raised to power k minus 1. Here minus 1. So up to so on. Here 10 times a1. Here just minus of a1. So again a1 is common. And here multiple is 10. Here multiple is minus 1. And plus. So remaining plus 3 times m. Okay. How we get this? By putting the value of a naught, this value, by putting the value of a naught in the general representation of here, we get this. And we will make some adjustment. Now, there is one rule. That rule is we always divide 10 raised to power k minus 1 for k greater equal to 1. Now see, if k is equal to 1, k minus 1 is 9, k divides 9. If k is equal to 2, 10 raised to power 2 is 100 minus 1, 99, k divides 19 up to so on. This is the general rule. So we always divide 10 raised to power k minus 1 for k greater equal to 1. So this rule suggests that 3 divides this term, 3 divides this term, 3 divides this 10 minus 1 also, and 3 also divides 3m. Okay. So the rule is we know that 3 always divides 10 raised to power k minus 1 for all k greater equal to 1. 3 divides this term, 3 divides this term, 3 divides this term also, and also last term is 3 times m, multiple of 3. So 3 divides each term. This applies 3 divides. Okay. So you can write here if only. Okay. So 3 divides, we are maintaining our sequence from this. So 3 divides this, if only this is multiple of 3. If only value of a naught is this. Okay. Now putting this value of a naught, we get this. So we have 3 divides 10 raised to power k minus 1. Okay. That is now from this equation we see 3 divides each term in RHS. Okay. Now 3 divides each term on right hand side. Okay. 3 divides 3m, 3 divides 10 minus 1, 3 divides 10 square minus 1, and up to 3 divides 10 raised to power k minus 1. So since 3 divides this term, 3 divides ak into 10 raised to power k minus 1, 3 divides this term up to so on. 3 divides this term on the RHS. And RHS same as here. This happens. So only 3 divides here. Okay. So 3 divides sum of the digits. If only 3 divides here. This is the test of divisibility for 3. For example, consider the number 135. Okay. Now sum of it 1 plus 3 plus 5 is 9. 5 plus 3 8. 8 plus 1 9. And 3 divides this sum 1 plus 3 plus 5. 3 divides 9. So 3 divides 135. This is the test of divisibility by 3. Okay. Now here 121. 2 and 1 is 3 and 1 is 4. 3 does not divide 4. So 3 does not divide the 121. Okay. This is the use of divisibility by 3. Okay. Now we'll go ahead. Okay. Next stage is divisibility by 4. Okay. And the test is 4 divides m if only 4 divides the number formed by last 2 digits of m. Okay. That is 10 times 7 plus a naught. So we will give proof first. Okay. And then we will take some example. Okay. Again we know the general representation of n. N is equal to ak 10 raised to power k plus ak minus 1 10 raised to power k minus 1 up to a1 into 10 raised to power 1 plus a naught. But we know that 4 always divide 10 raised to power k for k greater equal to 2. Only for k is equal to 1, k is equal to 0, 4 does not divide 10 raised to power k. For k is equal to 0, 10 raised to power 0 is 1, 4 does not divide 1. For k is equal to 2, for k is equal to 1, 10 raised to power 1 is 10 and 4 does not divide 10. But for k is equal to 2, it is 10 raised to power 2 100 and 4 divides 100. 4 divides 10 raised to power 3, that is 4 divides 1000 also. So 4 divides 10 raised to power k for all k greater than equal to 2. So here is a naught. Here is 10 raised to power 1. So 4 does not divide 10 raised to power 1. So we don't know whether 4 divides this term or not. Whether 4 divides this term or not. But here next term is a2 10 raised to power 2. So 4 divides 10 raised to power 2. So 4 divides 10 raised to power 2 into a2. Next term is a3 10 raised to power 3. Again 4 divides 10 raised to power k for k greater equal to. So up to so on. Then all terms from this a2 10 raised to power 2 are divisible by 4. Only problem is about this last two terms in this summation. Okay. So this applies 4 divides m. If only 4 divides this 10 times a1 plus a0. That is the number formed by last two digits. For example, let's take the example 128. Okay. Now the number formed by last two digits is 28. Okay. 10 times a1 plus a0 means we can write 120 as 100. That is 1 into 10 raised to the power 2 plus 2 into 10 plus 8 into 10 raised to the power 0. But 4 divides 100. Okay. So 4 divides this number. If only 4 divides this number, that is 10 into 2 20 plus 8, that is 28. Number formed by last two digits. We know 4 divides this 28. This implies 4 must divide 120. This is the divisibility by 4. Okay. Now divisible by 5. We all know it. A number is divisible by 5. Unit place or unit digit is either 0 or 5. So 5 divided n. If only unit digit is 5, is 0 or 5. Okay. Again, proof is very simple. We have again same any number can be written as ak 10 raised to power k plus ak minus 1 10 raised to power k minus 1 up to a1 into 10 plus a0. Again rule, we know that 5 divides 10 raised to power k for all k greater equal to 1. 5 divides 10, 5 divides 100, that is 10 square. 5 divides 1000, that is 10 cube. Only 5 does not divide 10 raised to power 0, that is 1. Okay, so 5 divides 10 raised to power k for all k greater equal to 1. So 5 divides 10 times a1, 5 divides 10 raised to power 2 into a2 up to so on. 5 divides this term here. Only problem is about a0. Okay, so from this 5 divides here, if only 5 divides the last term in the summation, that is 5 divides a0. Okay, this implies a0 must be equal to either 0. Since 5 divides a0, a0 is multiple of 5. So either, and a0 is a unit place digit, that is single digit. This implies either a0 is equal to 0 or a0 is equal to 5. There are only two options, from 0 to 9 to the number divided by 5. So either it is 0, because 5 divides 0 and 5 divides 5. Okay. This applies 5 divides n. If only unit digit, that is a0, is either 0 or 5. This is the divisibility by 5. Okay. You will see divisibility by n. And it is very much similar to the divisibility by 3. Okay. So a number is divisible by n if only a number is divisible by 9 if only 9 divides sum of the digit. Okay. Up to 6. The text is very much similar to the divisible by 3. Okay. Now we will do a proof. Again, we know any integer or number can be represented as ak 10 raised to power k plus a1, sorry, a k minus 1 10 raised to power k minus 1 up to a1 in 10 raised to power 1 plus a0. Okay. So suppose 9 divides sum of the digits. Okay, so 9 divides this sum of digits a0, a1 up to so on. 9 divides a0 plus a1 up to AK minus 1 plus AK. Okay. Now 9 divided this sum means this sum is equal to multiple of 9, or there is some integer such that a0 plus a1 plus ak minus 1 plus ak is equal to multiple of 9. Okay. Now again we can write this as maintaining a0 to the LHS as we had done earlier in case of the divided by 3, maintaining a0 to the left side. Okay, and this is equal to this 9m as it is. Okay, minus this a1 minus a2 up to minus ak minus 1 and minus ak. Okay, now put this value of a0 in our general representation of the number. Okay, so we get n is equal to this ak 10 raised to power k as it is plus ak minus 1 10 raised to power k minus 1 as it is up to this a1 into 10 raised to power 1 as it is plus a0. Replace a0 with this value, so we get 9m minus a1 minus a2, okay, up to minus ak minus 1 minus a. Okay. Again here ak 10 raised to power k, here minus ak minus 1 10 raised to power k minus 1 minus ak minus 1 up to so on. So we know this is equal to 10 raised to power k minus 1 into ak. If you are taken ak common, ak is here, multiple is 10 raised to power k, ak is here, multiple is minus 1, okay, plus again 10 raised to power k minus 1 is common for ak minus 1 and here is minus 1, so minus 1 into ak minus 1 up to so on. Here is a1 times 10, so 10 is common, so a1 is common, so 10 is here. Here is only minus of a1, so only minus 1 is the coefficient. For here is a1, here is a1, so a1 is common. Okay, and at last plus 9 times m. Now see, we know the rule. The rule suggests 9 always divides 10 raised to power k minus 1 for all k greater or equal to 1. Okay, 9 always divides 10 raised to power k minus 1. So 9 divides 10 minus 1, which is 9. 9 divides 10 raised to power 2 minus 1. Then 100 minus 1, which is 99. 9 divides 999 up to so on. So each 9 also divides 9m. So each term is here is divisible by 9. This implies 9 divides here. Okay. So we have started with 9 divides the sum of digit and ended with 9 divides here. Okay. So the element or number is divisible by 9 if only sum of digit is divisible by 9. Okay. For example, take example 180. Okay. The sum of digits 8 plus 0 plus 1 is 9. This number must be divisible by 9. Okay. And we know 20 into 9 is 180. So 181 divided by 9 is equal to 20. So number is divisible by 9. So the number is divisible by 9. Sum of digits is divisible by 9. Okay. Here sum of digit 1 plus 8 plus 0 is 9. Which is divisible by 9. So this number is divisible by 9. Okay. 180 is divisible by 9. Okay. And for your reference, keep one more test in your mind. Is divisible by 11. Okay. I will directly give you an example. First, a number. Suppose there is number 121. Okay. So this. Suppose this is the first digit. This is second digit. This is third digit. If sum of digit at even place, if difference between sum of digit at even place and sum of digit at odd place is divisible by 11, then number is divisible by 11. Okay. Here sum of digit at odd places. Here this is odd place, so value is 1. This is odd place, value is 1. So sum of digit at odd places 1 plus 1 is 2. Is the difference with sum of digit at even place. There are only one even place. Second, there is no number at fourth place. So sum of digit at even place is 2. 2 minus 2 is 0. And 11 divides 0. This number is divisible as 0. So that this replaces what? 11. If difference between sum of digit at even place and odd place is divisible by 11, then the number is divisible by 11. Okay. For example, we will take now the number 2, 4, 3, 2. The sum of digit at odd place 4 and 2 is 6. 4 plus 2 is 6 minus sum of digit at even place. Second place 4 plus 3 plus 2 5. 6 minus 5 is equal to 1. 11 does not divide 1. So 11 does not divide this 2, 4, 3, 2 number. Okay. So this is the divisibility by 11. If you find also this is also. So thank you.